All right, today in Chem 100, last time we met, introduced topics of acids, bases, and pHs. And this is in your chapter 16 with a little bit of chapter 17 for the purposes of understanding equilibrium. Today, you'll notice in your schedule in the syllabus, today is scheduled as a buffer day. But instead of, well, actually, the buffer day was intended to take overflow from introduction of the chapter. And since the chapter's already been done, I'm going to use today for the next class session. I'm going to pull it forward and do the review using the review document. That will give you two extra days. Actually, this is Thursday, so it'll give you an extra 5 days. And then on Tuesday, next Tuesday, I'll do a question and answer session. I'll just zoom in for the first 30 minutes and see if anybody shows up. If nobody shows up, then I'll shut down. And then the following Thursday, a week from today, we'll have the exam on this material. And introduce the last, I think the last chapter. Yes. So we got one more chapter to do, exam 9 material on oxidation and reduction and electrochemistry. Okay, so I've got some of these questions in your review document marked off, and we're going to just look at those in order. Starting with number 3. Which of the following is the strongest conjugate acid? Okay. When we want a strong, let's see. If you're thinking of a conjugate, think in terms of products. So a conjugate acid would be the product of a base. So if we have products on this side, we're going to have an acid. We're going to have a conjugate acid derived from a base. Okay, so that means that the base is over here and it reacts with water. And a proton is transferred to the base. According to Bronsted and Lowry, bases are proton acceptors or hydrogen acceptors. So it accepts one from there, and that produces a positively charged conjugate acid. This is the base. This is the conjugate acid. And that leaves behind hydroxyl, which is the conjugate base. Right? So this would be the acid in this case. It's the proton donor. This would be the conjugate base. Okay. Now, we've introduced the concept of strength of acids and strengths of bases. But this is a different twist on the topic. If you want a strong conjugate acid, that means you need a weak base from which it is derived. So this would be a weak base. Okay? So when we look at these choices here, we have hypochlorous acid, we have hydrocyanic acid, we have hydrofluoric acid, and we have ammonium ion. And then all of these as choice, which is neither here nor there. So which would be the strongest conjugate acid? Well, we have to think about this one. If we start from the bottom, this one would be having a hydrogen here like that, right? You could write it that way. That means that this ammonia part would have been here, right? So what that means is, the question is then, is this a weak base, right? Does it prefer to be over here rather than over there, which would make that a strong conjugate acid? Well, we know we characterize ammonia as a weak base. And we can do calculations which are not appropriate for this course, but we can do calculations that prove that when you dissolve ammonia in water, 99.6% of it is that form. That means that it is a weak base. That makes this a very strong conjugate acid, the ammonium ion. So this is a good candidate. All right, what about these guys right here? That's an acid, acid, acid. Well, we know these to be weak acids. These are all weak acids. We're looking for a strong acid. Now, these would only be conjugate acids if we consider the base. And the base for each one of these would simply be what's left over after the hydrogen ion is gone. If these are weak acids, then these are very strong bases. And strong bases don't produce strong conjugate, strong bases do not produce strong acids. So we found our answer is ammonia. Better. Not the best. All right, number 4. Calculate the hydrogen ion concentration, the equilibrium concentration of hydrogen ions in a solution that has a pH of 8.82. So if the pH equals 8.82, that has to be derived from the negative log of the hydrogen ion concentration. Okay, so we know how to do the antilog of the negative. All right, we move this negative over here. Okay, and then we say, what's the definition of a log? This value is the power of 10 that will give you that value, which means that 10 to the minus 8.82 equals the hydrogen ion concentration. So all we need is a calculator. And let's see, 8.82 and change the sign and then do the 10 to the x. And that is 1 point, let's see. We have 2 decimals, so we can have 2 significant figures here. 1.5 times 10 to the minus 9th molar. Okay. Right. Number 5. A solution is prepared by dissolving 111.9 grams of hydrogen chloride gas in enough water to make 160 liters of the solution. The pH of the solution is. So what we're given is the mass of hydrogen chloride is 111.9 grams. Okay. And the volume, the final volume is 160 liters. Okay. Can we calculate the pH of this solution? Not with that data. We have to transform it. We need moles per liter to give us the molarity of hydrochloric acid. Then we can find the pH. So this has to be converted to moles. Right? Grams, top, bottom, they cancel. So what we need is the molar mass of hydrogen chloride. 1.01 for the hydrogen and 35.45 for the chlorine. That's 36.46. That will tell us the number of moles of hydrogen chloride. I get 3.0691 moles. Now we can calculate the molarity. The molarity then would be 3.0691 moles divided by 160 liters. Now this is this needs to be rounded off eventually to 4 significant figures. I'm keeping an extra one just to avoid rounding error. So divide by 160 and I get 1.9182 times 10 to the minus 2 molar. And 4 significant figures would be right there. So we have 1.918 times 10 to the minus 2 molar hydrogen ions. Now, how do I know it's hydrogen ions? Because for every 1 HCl, we get 1 hydrogen plus the chloride. So it's a 1-to-1 relationship. If I know that concentration, I also know this one. Now we can calculate pH. And we also know that since this is a very strong acid, it goes virtually to completion to the right. In other words, there's none of that left over. All right, so what do we get from this calculation? Let's see, I take the log of that value and change the sign. So I get 1.717107. All right. So we've got 4 significant figures. We can have 4 decimal places. 1.7171. Yeah. Now the answer may not be exactly like that. It looks like they rounded it off. They rounded that off to 2 decimal places, which would be 2 significant figures. But technically we have the numbers tell us we have 4 significant figures, which means 4 decimal places. Right? So in that case, pick the best answer. And I suppose you could say none of these, since 1.72 is not exactly 1.7171. But if you take the exam and it marks it, if you say none of these and it marks it wrong, then you've got to come back and prove that why you chose that one and not 1.72. So you may just want to take 1.72 as the answer. Let it go at that. Number 6. A solution has hydroxide ion concentration at equilibrium of 5 times 10 to the minus 4th molar. The pH of this solution is. All right. So we're given the equilibrium concentration of hydroxide ions as 4 times 10 to the minus 5 times 10 to the minus 4 molar. You have two options here. You can use Kw equals hydrogen ions times hydroxide ions. And this is 1 times 10 to the minus 14. And insert the value here and solve for that one, and then take and calculate the pH. Or you can calculate the pOH. pKw equals pH plus pOH. And this would be 14. I prefer the second method. So if we take the negative log of 5 times 10 to the minus 4 and find out what the pOH is, which is, let's see, 2 significant figures. 3.3 equals pOH. Then the pH equals 14 minus 3.3. And 14 is an exact number. So we're only limited by this one. And 14. Oops. Which is 10.7. Which is the pH, 10.7. Okay, so they're saying 10.70. Oh, yes. 2 significant figures. Sorry. 2 significant figures. 7. Oh. There you go. In fact, this should have been 3.0. Like that. Okay, 6. Take a look at 7. As water is heated, its hydrogen ion concentration increases. What does this mean? So we start off with a certain concentration of hydrogen ions. And as you heat water, and we're talking about pure water here, as you heat water, it produces hydrogen ions and hydroxyl ions. Okay? So as you, let's see, increase the temperature, you get more hydrogen ions. All right. But what else do you get? As you heat it up, you get the same number of hydroxyls as hydrogen ions, right? Yeah, because they come from the same place. So what does that mean? Well, is this water neutral, acidic, or basic? It's neutral because the hydrogen ion concentration equals the hydroxide ion concentration. That equals neutral. So we know that one is right. A is correct. Hydrogen ion does not exceed hydroxyl. Hydroxyl does not exceed hydrogen. Hydroxyl also increases. Yes. So A and D are both true. Now, at 25 degrees, this concentration is going to be 10 to the minus 7th molar. Right? As we heat it up, the concentration is going to go higher. I don't know what it is, but it'll be greater than 10 to the minus 7th. But the concentration of hydroxyl will also be that same concentration, which means the solution is neutral. Number 8. Identify the Bronsted acids and bases in the following equation. A is a Bronsted acid, B is a Bronsted base. Okay, so let's write the equation up here. HSO3 minus, which is the hydrogen sulfite ion, polyatomic ion, cyanide ion, then hydrocyanic acid. And we have to assume that all of this is occurring in aqueous solution. With the sulfite ion. Okay. So in terms of Bronsted and Lowry, on this side, we start on this side, which one donates a proton? If this one loses that proton, there you go. So this one is the proton donator. That makes it an acid. That means this one has to be the base. This one receives. Okay, so now this is the conjugate base. And this is the conjugate acid. So using the symbols that the problem gives you, this would be A, this would be B, this would be A, and this would be B. All right, so AB is the answer, which is option B. Okay, number 9. Which of the following is a conjugate acid-base pair? All right. If we're saying acid and its conjugate base, that means that we've got to pair them up like this. Now, this could be charged, right? But the difference is this one is missing one proton from this side. So we have to look at our choices and see which ones satisfy that condition. So we've got HPO4 2 minus, HPO4 yeah, 2 minus, and then PO4 3 minus, and then HNO3 minus, okay, and H2NO3 HNH4. Right, and HF minus H2 and minus. All right. Hands off, I did not create this problem. This particular question is just completely ridiculous. And the reason I say that is some of these compounds that are represented here do not exist. They cannot exist. This one is correct. That one does exist. This one does without a charge. And this one's okay. Yeah, that one's real. And these two are real. But the rest of these, this one does without the charge. The rest of them cannot exist, at least not in my universe. But even if they did exist, we look at the acid base, right? If we take one of these hydrogens away, we'd have an NO3, right? That can't work. If we take one of these hydrogens away, then we get this one with should be a minus, not a plus. So that one can't be. If we take one hydrogen away, then HF minus, right? If we're just being technical about it and not worrying about the chemistry, that's possible. You know, the problem is neither one of those exist. And this one has lost 2 hydrogens. So this one can't be it either. Right? Our best choice is this one right here. If we lose 1 hydrogen and leave the electron behind, right, because it would have this out here, then we increase this one, go from a 2 minus to a 3 minus. So A is your best answer. And when you're in a testing situation and you're taking multiple choice tests, you always pick the best answer. It may not be exactly the one you were looking for, but it is the best one. And A in this case is the best answer for that group. All right, number 11. Is that right? No? Oh, I scrolled. Number 10, excuse me. Choose the case that is not a Bronsted conjugate acid-base pair. All right, so this one flips it on its head, turns it around the other way. So we've got these choices. And the first one is HCN and CN minus. Is that an acid-base pair? Yeah. We lost 1 proton and ended up with CN minus. That one's a good one. How about CH3 NH3 plus? And CH3 NH2. CH3 NH2. All right. Where would the proton come from? It didn't come from this side, it came from this side over here. So if you lose 1 proton, it takes that positive charge with it and leaves the neutral behind. So this one's good also. How about C? HCO2H. HCO2H and HCOH. HCOH. All right. Notice what we've lost here. We didn't lose a hydrogen. We lost an oxygen, right? So That one won't work. And D is H3BO3, and it's probably H2BO3 minus. Yeah, that one's good. And HClO2, and this should be ClO2 minus. Yep, that one's good. So C is the one that shouldn't be there. It violated the rules. Now number 11. Calculate the hydrogen ion, excuse me, concentration in a solution that has a pH of 9.16. We've done one like this before. So if the pH is 9.16, right, that's equal to the negative log of the hydrogen ion concentration. So what we want is 10 to the minus 9.16. And that should give us our hydrogen ion concentration. And let's see, two significant figures. 6.9 times 10 to the minus 10 molar. Okay. That was fairly easy. Okay, who's next? Skip down a little bit to 15. Calculate the pH of an acid solution containing 0.044 molar HNO3. 0.044 molar HNO3. And we want the pH. Is that a strong acid? And I'm talking about so strong that it produces that plus that. And there's nothing of that left. If that's the case, then this concentration is the same as that concentration. Okay? 0.044. And take the log of it, change the sign. So two significant figures. So this is 1.36 pH. Okay. Okay, we got another one. Very much like that one. Only this time it's 4.9 molar perchloric acid. 4.9 molar perchloric, which is a strong acid. It's going to produce hydrogen ions plus the perchlorate ion. So this is actually the concentration of that one. All right. So brace yourself. This is probably going to be a negative value. Negative log of 4.9. And we have two significant figures. This is minus 0.69, 2 decimal places. Okay. All right. Go to 17. What is the pH of a 0.25 molar nitric acid solution? Oh, we're getting a lot of repetition here. 0.25 molar nitric acid, HNO3. Strong acid, so the negative log of 0.25 equals 0 point, let's see, two significant figures. So we have 6, 0. That's the pH, 0.60. Yeah. I think the point of these two problems, 16 and 17, is to emphasize the fact that this is a mathematical transformation. You could end up with almost any number, as long as these numbers are valid, chemically speaking, then this is simply a calculation. About 18. A solution has a pH of 3.16. pH 3.16. And the question is, what's the pOH? The simplest answer to this one is 14 minus 3.16. Right? So that'd be, let's see, 4, 8, and 3 from 13 is 10. 10.84 pOH. Okay. All right, let's look at 20. Which of the following is true for a buffered solution? Okay. Talking about a buffered solution. Okay. Let's see. The statements look like they have several parts to them. So one part might be true and another part might be false. So every statement or every phrase within that statement must be true. What's true about a buffered solution? The first one says the solution will not change its pH very much, even if a strong base is added. That is true. B says the solution resists any change in its hydrogen ion concentration. That's also true. That's definition of a buffer. Any hydrogen ions added will react with the conjugate base of a weak acid already in solution. In most cases, yes. The conjugate base of a weak acid? Yeah. Because the conjugate base of a weak acid is a strong base, and strong bases are looking for hydrogens. All right, so when you add that hydrogen, that conjugate base is going to scarf it up. That means pH doesn't change much. That one is also true. The solution will not change. This is D. Very much. Its pH will not change very much, even if a concentrated acid is added. Well, yeah, that's true. You know, up to a point, right? There's a concept that we didn't discuss in class called buffer capacity. Now, as long as you are able to stay within the buffer capacity, then all of these statements are true. But once you exceed the buffer capacity, then it's no longer a buffer. But as long as you're within that capacity, then the buffer will function as A, B, C, and D. So all of these are true. Oh, got a zoomer. Okay. Let's see, number 20, I got highlighted number 24 next. A solution has hydroxyl concentration of 3 times 10 to the minus 7th molar. The hydrogen ion concentration in this solution is such. Okay. So we have, this is given to us 3 times 10 to the minus 7. Okay. The simplest way to answer this one is to go back to the equilibrium expression. Right? Kw equals 1 times 10 to the minus 14, which is equal to hydrogen ion concentration times hydroxyl concentration. We got that one. We got this one. Any equation with one unknown can be solved. So let's just substitute what we know here. 3 times 10 to the minus 7. And that means that the hydrogen ion concentration equals 1 times 10 to the minus 14 divided by 3 times 10 to the minus 7. Right? So I don't need my calculator for this one. 1/3 is 0.333. Well, let's see. We got two significant figures. I better stop it there. Times 10 to the minus 7. Right? Because minus 14 plus 7 is minus 7. And then we straighten this thing out, scientific notation, 10 to the minus 8. So 3.3 times 10 to the minus 8 is D. That's molar. Okay. You can use your calculator if you want, that's fine. I do it in my head when I can, just to keep my brain cells working. All right, let's see. Who's next? Highlighted 27. A weak acid, hypochlorous acid, okay, is in solution with dissolved sodium hypochlorite. So it's in solution with sodium hypochlorite. Okay, these are both aqueous. And what else are we given? If hydrogen chloride is added, which ion will react with the extra hydrogen ions from the hydrochloric acid to keep the pH from changing? All right, if we look at this problem, if we put these two together in solution, this one is going to dissociate into hydrogen ion, sodium ions and hypochlorite ions. So in solution, we're looking at this acid in this base. Okay. Now, if we write it the way that it actually happens in solution, we put a water here and hydronium there. Or if we want to write it in simple form, simplified form, for calculation purposes, then this will work just fine. Okay, so when we add acid to this, if this is a weak acid, and we know it is, that means this is a strong conjugate base. And if we add hydrogen ions, where are they going? Hydrogen ions here come in here. According to Le Chatelier, it forces the reaction back this way. So the hydrogen ions are going to be picked up by the hypochlorite ion, and that's D. There it is. No. Oops. No, it's not working. Thought I could highlight it. There we go. Picked up by this one right here. All right, next. 28. Which statement is true for a strong base solution with a concentration greater than 1 molar? Okay, strong base. Let's see. Let's make this real. Let's say it's sodium hydroxide. We know that's a strong base. And if it's 1 molar, right, it could be potassium hydroxide, or it could be lithium hydroxide or rubidium hydroxide. They'd be good, strong bases. With a concentration of 1 molar. Well, we know that this is going to go to sodium plus hydroxyls. And the hydroxyl concentration is going to be 1 molar because strong bases completely dissociate in water. Right? So let's look at our choices. pH is greater than pOH. What does that mean? pH is greater than pOH. If pH is equal to pOH, we have a neutral solution. If pH is high, remember, pH runs in the opposite direction to the hydrogen ion concentration. So we increase the hydrogen ion concentration, pH goes down. That's toward the acidic. So if pH is greater than pOH, this is basic. Definitely basic. And that's true. That one's definitely true. pOH is greater than pH. Well, it can't be both. You got to have one or the other, right? So that one can't be it. pH is less than 14. pH is less than 14. Well, how would we answer that question? Well, we would do the pOH, right? pOH equals the negative log of 1, right? So 10 to what power is 1? pOH is equal to 0. And pH equals 14 minus 0, which is 14. So pH is not less than 14, it's equal to 14. And the last one, pH less than 0. pH less than 0. Well, we already calculated the pH as equal to 14. It's not less than 0, right? So that can't be it. And the last one says 2 of these. No, only one of them was true. This one right here. A is the only true one in that state, in that list. All right. Let's see, 30. Okay. A solution with a pH of 2. Say we have a pH of 2 in our solution. Is how many times more acidic than a solution of pH 6? So this is pH 2 versus pH 6. Right. Remember that pH is a logarithmic progression. So that means it's powers of 10. If we go from 2 to 10, it's toward the basic. If we go from 6 to 2, how many times more acidic is this one? Well, the difference is 4, right? 6 minus 2 equals 4. So 4 is 10 to the 4th power. That's what we're saying. The difference in pH of 4 is 10 to the 4th power times more acidic, which is 10,000. Right? 10,000 times. That would be D. All right, 32. Buffered solution contains HNO2. All right. HNO2. If that's the buffered solution, is that a weak acid? Yeah, HNO2. Nitrous acid. This is nitrous acid. And it is weak. So if we're going to use that in our buffer, what we probably want is the conjugate base of this, which would be NO2 minus. That's our base. Okay, so in this case, how do we get that in solution with this? We need to put this into solution with a soluble salt, right? Some metal ion with NO2 will produce, right? And that gives us this in solution. So we combine this with some salt of the NO2 so that we get, and in fact, the best position for this buffer would be equal concentrations. HNO2 concentration equals NO2 minus. That is right in the middle of the buffer zone when these are equal. And the way you get that one in solution is you put it in there as the salt of that anion. So the only one that gets you there is A, KNO2. So we make that a K. This becomes potassium. And that's how you do it. 33. Consider the reaction. That looks like acetic acid. HC2H3O2. And then water. Yep. What are we going to get? Well, we're going to transfer a proton from here to here. C2H3O2 minus plus the hydronium. There we go. Okay. Well, I wrote it backwards. They put this one first. Which species is the conjugate acid? Well, if this is the weak acid, this must be the conjugate base. That makes this the base because it receives the proton. That makes this the conjugate acid. All right. And the question was, which is the conjugate acid? H3O plus. That's the conjugate acid. 35. Which of the following is not a conjugate acid base pair? All right. B, C, D, and E. So the first one is H2SO4, H2SO4, and I write it like that with a slash, SO4 2 minus. Is that a conjugate acid base pair? No, because you've got a difference of 2 protons. You can only have a difference of 1. How about the second one? All right, acetic acid and C2H3O2. Oh, the question was, which is not a conjugate acid-base pair. All right. Got to read the question. This is not a conjugate acid-base pair. This is acid-base pair. How about this one? HNO3 and NO3 minus. Yep, that's a conjugate acid-base pair. Doesn't answer the question. H2PO4 minus and HPO4 2 minus. Yep, that's a conjugate acid-base pair. And the last one. HBr and Br minus. Yes. Right. So the only one that is not a conjugate acid-base pair is the first one. Okay. 37. All right. Given the following list of Kas, which of the conjugate bases is the strongest? All right. So rather than write all those up there, let's look at the Kas. What does the Ka mean for an acid? The larger the Ka, the stronger the acid. So let's look at the powers of 10. All right, we've got -4, -8, -10, and -10. We're looking for the strongest base, the conjugate base that's the strongest. So we want the weakest acid. All right, we've got the top one, ammonium and hydrocyanic have the same powers of 10. So we go to the coefficient and compare. And we find that the weakest, the weakest acid is ammonium ion. So it would make the strongest conjugate base. So what's the strongest conjugate base of NH4 plus? This is the acid, right? Transfers a proton and makes this conjugate. This is the base. This is the conjugate acid. This is the conjugate base. And this would be the strongest conjugate base of that list, in that list. We're not saying it is the strongest of ever, but it's the strongest of that list. All right, so NH3 would be the one we're looking for, and that's C. Okay? Strongest conjugate base out of that list. Let's see, here's another one, 40. Solid calcium hydroxide is dissolved in water until the pH of the solution is 10.39. Okay. Solid calcium hydroxide. It's dissolved in water. And what that produces, we're going to simplify this. And this is going to produce, actually, that's a strong base. So it's going to produce all of that as calcium 2 plus 2 hydroxyls. Okay. Until the solution is 10.39 pH. pH equals 10.39. That's everything we're given. The hydroxide ion concentration is what? Well, we know what the pH is. What's the pOH? The pOH is equal to 14 minus 10.39. Right? So that would be 1 and 3 from 9, 6, and 10 from 13, 3. That's POH. Well, what is that equal to? That's equal to the negative log of the hydroxide ion concentration, right? So 10 to the negative 3.61 will answer our question. Change the sign. 10 to the x. Let's see, we have we get two significant figures. So 2.5 times 10 to the minus 4 molar. That would be B. Number 41. Choose the pair of concentrations that cannot be in a given aqueous solution at 25 degrees. All right. So we got pairs of hydrogen ion and hydroxide ion concentrations. So let's do it like this. We got hydrogen ion concentrations in this column and hydroxide in this column. So we got 10 to the minus 13 molar and 1 molar and 10 molar and 10 to the minus 15 molar. And C is 10 to the minus 3 molar and 10 to the minus 11 molar. And then 10 to the minus 7 molar and 10 to the minus 7 molar. And the last one is all can exist. So all we have to do is find one that cannot exist, and that knocks E out also. So what are we looking for? Well, if we multiply these times each other, they should be equal to 10 to the minus 14. Right? This is K W. So this one times this one equals that. Is this true? Well, 10 to the minus 13, and what's 1? It's 0, isn't it? 10 to the 0 is 1. So if this is 10 to the 0, then minus 13 plus 0 is not minus 14. So we found one, we can knock that one out. But there are no others that say A and B are true or C and A, right? So if you're in a hurry in an exam, we found our answer. But if we look at this one, 10 to the 10 to the first power, minus 15, yes, that's true. 3 and 11, that's true. 7 and 7, that's true. So A is the only one that's wrong in that group. Let's do 42. What's the pH of a solution mixing 96.1 grams of sodium hydroxide, 96.1 grams of sodium hydroxide, in enough water to make 3.2 liters? So this is the mass. This is the volume. 3.2 liter, was it? Yeah. 3.2 liter. Right. We've got to be able to calculate the hydroxide ion concentration in order to determine the pH. Now, we know that if we have 1 mole of sodium hydroxide, dissolve it in water, you get 1 mole of hydroxides. So if we convert this to moles, then we can tell how many moles of hydroxides we have. What we need to do is convert, right? Numerator, denominator. Now we're left to moles. What we need is the molar mass of sodium hydroxide. So sodium is 23, right? Oxygen is 16. Hydrogen is 1.01. Let's see, that's 40.01 grams per mole. So that's 96.1 divided by 40.01. And that's 2.402 moles. I'm keeping extra decimals to avoid rounding error. So the hydroxide ion concentration then is equal to 2.402 moles per 3.2 liter. Okay. So now I can round it off to 2 decimal places. 2 significant figures. 7.5 molar. Okay. Now we want to calculate POH, which is the negative log of 0.75. Okay, 75 and do the log, change the sign. So that's 2 significant figures. I get 2 decimal places, and that's 0.12. POH, right? Check yourself. Yeah. So pH equals 14 minus 0.12, which would be 13.88. Yep. So that's the pH. Let's see, I didn't write that correctly. Small p, big H. There we go. That's 42. Next, let's see, scroll. Oh, that's it. Those are the only ones that I had highlighted. If you have any others, Olivia, we can look at them. Any of the ones that I didn't highlight. And let's see, you came in at about right in this neighborhood, I think. So if we look up here, I did 20, 18 back up through 15, 11 through 7, 6 through 3. So any of the others, we can do them if they're giving you trouble. If not, then this concludes the review for exam 8 on chapter 16, acids, bases, and pH. And since the exam is scheduled for a week from today, which would be Thursday, the next Tuesday, which in the course schedule would be the review. I did the review today instead of then because today's a buffer day. Then I'll just zoom in on next Tuesday for about a half hour and see if anybody shows up with questions. And if nobody does, then I'll drop out, and the exam will be on a week from today, that Thursday. And we'll also introduce the last chapter, which is on oxidation reduction and electrochemistry. And then that will be the last chapter before the end of the semester.